honestly, I don't, maybe we did.
I feel like you told me, it was like after the, no, it was Monday. It was Monday, that's right. Because you told me afterwards, like, oh, did anyone come by the class that you?
Yeah, that's right, we did talk about it, okay. Yeah, Monday. Yeah. That's right.
Is that right?
You ever figure it out?
I was just looking at what he did. I don't know. Totally fair.
So, we'll talk about this in a moment. So the solutions I showed on Monday, I don't know what the hell I did with them.
Oh,
Solve it again. I mean, I had like too many places where I think you should put in notebooks, I just, I don't know where it is. So, I'll have to do it again, or maybe copy one of your solutions and post it, because it was, just in general, I don't know what's going on with the wiki, and no one in UTS is able to figure it out. But if you look in the Dropbox, everything is there, and if you want to see the videos, just go on YouTube, my YouTube channel, I'm posting it there so you can see it. So until I figure out what the hell is going on, and or set up my own webpage or something for the class. So I'm going to give it another week. If you can't figure it out, I guess I'll set up a webpage, or we can run our own
We can use
wiki.
the domain, yeah.
Yeah, you can use Omega too.
Yeah, exactly. So
Yeah.
I just set up a page. I just wiki, I thought it was easy, and that's what it's for, right? It makes it easy. Right. So, but anyway, everything is in the Dropbox, and I'm being good about it. I mean, even the lecture notes about what I'm going to give them now is in the Dropbox. Okay. Okay, I'm just going to start. I don't know why people aren't here. So on Friday, we have a department retreat. We're going to work on a strategic plan of the department. So I can potentially leave that because this class is near the end of that, but it'll be probably better for me to stay. So what I'm going to do is defer the lab until Friday. So you guys can work on it on Friday. What I want to do today is I want to get started on probability theory, and I'm actually going to give you a lecture on the board. I recommend that you guys take notes. If you didn't bring paper, I brought paper to you for your own sake, okay? But before we do that, hold on, before you go to your laptop, just a second. But I just one second. And the notes are already posted. They're already in the Dropbox. And as I said, the Dropbox is okay. It's up to date. I don't know what's going on with the wiki. I can't log in. Once I can, I'll update that too. But everything is in the Dropbox. All 5 lectures with the videos and everything. And the YouTube, you can just look me up on YouTube and you'll find all the lectures. I'm posting them. Yes, sir.
How do we get to the Dropbox?
If you go to the wiki, there's a link to the Dropbox there. So I can't update the wiki, but it still works. It's just I can't log in. Don't understand why. So then the other thing I was going to say is I've been a little bit lax and been saying, and I know people are have had trouble logging in and doing stuff. And I took snapshots when I said I would take snapshots. And I took a snapshot today already of what you guys have done. I'm being forgiving for now, but starting Friday, when I say something's due before class, or I'm going to take a snapshot at some point, I'm going to take that snapshot and gauge you based on that, okay? So any other issues you have about logging in or whatever, solve them today and deal with them now, okay? And I'm not going to give you anything extra. You have an opportunity to go back and take the last 2 labs and make them perfect, okay? So go do that by Friday before you come to class, and I'll take a snapshot right before class, okay? And then you'll have a new lab during class, okay? So that's the plan. Having said that, I went through the solutions with the other lab 1. As I said, it's fine for you to see the solutions, or even see the solutions with somebody else, as long as you go down and implement it yourself, so you learn how to do it. And I don't know what happened, but the notebook with the solutions got lost. But I will, at Friday, I'll write solutions again, and I'll post the solutions for that one. It'll be in the Dropbox directory for that particular, you'll find it. And today I'm going to show you the solutions for the lab that you were supposed to have done for today, just so you see it, but I won't post it. Go home and finish it, okay? And so it's there for Friday. So let's do that now. I heard that one or two of you are still having trouble logging in. I don't know, did you resolve that problem?
No, I didn't have that problem.
Oh, somebody.
I resolved the problem.
Resolved, okay, sorry. Okay, so let me go through the solutions really quick, and then I will switch. So you guys all read it. So I actually did it in steps. So it was a little bit harder than actually I thought. One thing you have to do, and it wouldn't matter for this particular one, but it ended up, so the way I did it was, I basically just tried operations. I looked at the answer isn't right, and I just kept on playing with it until I get it right. I know it's, it's, I guess I'm trying to get a sense of, it's good to go to visualize and write down the answer, but you don't have to do that. You guys, the way that I usually work is I'm not working in Jupyter notebooks, but I have terminals open. I always have a Python session open. Whatever I'm trying to do and code up, I do it on the Python prompt on a little example to see if it gives me what I want, and then I copy and paste the code into my actual piece of code that I'm going to run on the whole data. And so experimenting is not a problem. I think it's you should try it, and you can try it and see what you get. Then you get a sense of what these things do. Okay, so that's how I ended up actually getting this answer. So as I said, I knew that I had to reshape this thing. So I first did the reshape, but then I realized that when I did that reshape, what I wanted to do is sum on the columns. And if I did the reshape, what it will do is it would put this one next to this one. But what I want is put this next to that. I want to put the columns next to each other and sum them rather than the rows and sum them. So I did a transpose before that. Now, it actually didn't matter for the answer because this happened to be a symmetric matrix by accident. So it didn't make a difference, you'll get the same answer. But the right answer is to first do the transpose. Okay? I did a transpose, so I did the data and you do the transpose, it looks exactly the same. That's the transpose. And then I reshaped it so that what I did was I put those columns next to each other, the reshape, I summed, right? And then so that's the sum, and then I reshaped it back to the shape that I want, and that's the answer. Okay. So you have to use, it was a little bit trickier, you have to do a transpose, and you have to do a reshape at the end to get the thing back. And the answer should be, like, as I said, A and B should be combined, right? So the answer should have been 1, 0, this should have been plus, maybe I got the answer wrong. It should have been 1, 0, 1, 0, 0, 1, 0, 1.
So if we,
Yes, that's what I got, 1, 0, 1, 0, 0, 1, 0.
instead of transposing it, would it make sense to just reshape it to 2A and then sum over the columns?
The problem with reshaping is that the data is written sequentially like this. It's actually a good question to think about, right? The data, I'm going to right? The data in memory goes like this. So if I flatten the whole object, it'll be, this will be here, and then this will be after it. Right?
Right.
And if I do the other one, if I do A2, it'll be like this, right? So it puts this next to this. But what I want, so if I do it that way and sum that way, what I'll be summing here would be this with this. And that's not what I want. What I want to actually sum are these two columns, right? I want to say the sum of these two columns. So if I do it the other way, if I don't do the transpose, I sum rows. They may be, because they're reshape. Okay? And I can't think of any other way of doing it without because you have to do the reshape, but you have to do the reshape in the right way. I can't think of any other way of doing it.
I think I might just change the numbers so it's not symmetric and that's what
The answer would, yeah, yeah, that's possible. It just happened to come out the same
Yeah.
because it was symmetric. Okay. Is that everybody? Okay. There's going to be a lab on Friday instead of today, because we're going to have a retreat on Friday at the department. Just repeating. Everything is in the Dropbox. You can get the links from the wiki. I can't update the wiki. If you need the video, go to YouTube. They're all there also for all the lectures. So what I'm going to do is, I've been forgiving. On Friday, I will take a snapshot of lab 1 and 2 to make and grade you on that. Okay. So make sure you've done it before class. Okay. I'm not going to repeat myself. Okay, so then the second one, what am I supposed to do? Oh, so I was supposed to shift this, right? So one thing I did was I shifted it by the, so I said sigma, but really I mean variance. So what I did was, first of all, I calculated the variance of this thing just so we see it. I hadn't put it in there. You can get the variance this way. So the variance of this thing is 93 for my set of data that I ran data that I've made, right? Now, the variance is the square of the sigma, right? So this should be about 100, and the square root is 10, which is this. The variance is the width of that, the square of the width of the distribution, okay? So then what I want to do is to shift it by the mean and then divide by the variance in the right way, by the sigma. So that's what I did. I take the original data, I shift it by the mean. One thing that's subtle, maybe you notice, NumPy here, this is a tensor, and this is a number. So NumPy is smart enough to know you're going to do it to every element. Right? And then, so now it's giving me something that's centered around 0, but now it's too wide. It still has the same variance of 100 or sigma of 10. Then I divide by the square root of the variance, right? And so then I get something with a mean as close to 0 and the variance is, which is what I want. You guys see what I did? I shifted it, and then I divided by the width of the distribution, and it made it mostly between 0 and 1.
So what I was looking for whenever I was doing that one was like a way to go in and like directly change the variables that you input at the beginning. Is there no way to do that?
What do you mean directly change?
Because like you put 4, 10, and 100. If you want it centered at 0.5, you just put 0.5. And if you want it between 0 and 1, you just put 2 instead of 10.
Yeah, the whole point was, this is the data you're given. You weren't supposed
Right,
to
yeah,
change that.
I'm not saying I changed that.
I know, but
I'm
so
saying,
that's
is there
it.
like some sort of process that I can call on to directly change the inputs?
You can write this in a function, and then call it, and it'll do the thing for you. Is that what you mean?
Kind of, I guess, yeah.
Right? You can just call it a function. And you don't need anything. All you need is the data, because you can calculate everything from the data. Yeah.
Okay.
All right, and then, any other questions on that? So then the next one, different people can do it different ways, but this was to check the flatness of this thing, right? So all I did was, so I already had so I generated some flat distribution, I'll call that x0, and we already had that distribution x, the known distribution, I just use it again, okay? And here, I just wrote a function to check flatness. What I do is I find the minimum and maximum of the data. I'll step through it with the number of steps, so I have 10 steps. So my step size is I take the maximum and minimum divided by steps, that's the step size that I'm going to take, right? I have to do this funny loop because I can't read range. And then the whole trick here, a difficult part here, is I use np-where to identify the regions where, to get the ranges. Right? So what I'm doing is I find the step, the range of the data, I go through it and count the number of events, or number of entries. So I'm doing it that way. And I'm using the shape command. I should have said shape 0, shape 1, so it would be the first element, right? And you can see it's not doing a great job because it goes past the endpoint. I should have been more careful. But you can see that so this is from 0 to 0.1, 0.1 to 0.2, so on. There's roughly about 100 in each, right? There's 1,000 events. It's flat distribution, about 100 in each of 10 sub-regions. Makes sense, okay? And then you do the same thing with the Gaussian, and that's the Gaussian that's this one, this is pumped up with the Gaussian. And here you can see that it's all mostly distributed about the center. Right, which was it, right? There's more events in the set. Right?
So,
Yeah,
I think for the while, that part of the function,
yeah,
I think it's easy to use enumerate, right?
use what?
Enumerate?
Uh,
Right?
And Mueller, my problem is that I need to be able to do this, and not an integer set size. I don't know how to do that, maybe you can do it in Mueller, but I don't know.
Yeah, I think I used the same thing for previous lab,
Okay,
that I didn't know this, so I
Okay.
used enumerate.
I'll give it a try, actually, it wasn't good enough.
Yeah.
That's- Thank you. If I can do it that way, then it's prettier. And then the last one, actually, this is a pretty big file, so it takes a long time to load it. I was trying to do it. So the first thing I did, actually, oh, it's not in here, is I only asked for the first 10 images, just because I didn't want to load all of them. Okay, that's fine. We do something like that. And then I actually didn't get a chance to finish this one, so I'll let you guys work this out, how to do this one, okay, for Friday. Okay. Having seen all this stuff, struggle a little bit, see if you can figure out how to do it. Okay?
I think I have a test file for S5, or, yeah,
You got a small one?
yeah, I think.
And this works. I mean, if you just, it's the same thing. And it should work. Okay? So I do recommend that while you're playing with it, you pick just one or two events just to make it faster for the loops. Okay? All right, so that's a little walkthrough, so you get a sense. Let's go into the lecture. Yeah, so one problem is that this thing is not focused. I asked the guy to focus it, and he said he would, but he hasn't in 2 weeks. So I'm going to have to ask him again, I guess. So you're not going to be able to see. Let me try something. I wish I had started this earlier. I bought the camera, so I'm going to just kind of record myself. This way you guys can have a copy of what I'm doing on the board for the YouTube video, if I can get it to work. So give me 1 minute to try to get this to work.
You said you have a paper?
I have paper. I'll show you paper. Come to class without paper. Of course, I asked you guys to bring a laptop, but now it's the other way. All right. Okay, it's using that camera. Well, we have something, the camera of this thing is good enough so that I can get, I'll just do this. Separate. Looks like the camera of the. Okay, so what I want to start on is a introduction to sort of probability theory. It's going to be very basic, and here it's really, I'm trying to get your head around what we're talking about a little bit of formalism behind things. I'm not going to ask you guys to really do any calculations based on this stuff, but understanding these concepts are important. These notes that I'm using, I've actually given this lecture many times, and so I just pulled it from some other place. These notes that I'm using, it's in the Dropbox, so you can just go there if you need to. So what I want to talk to you about here is, we want to do this in the context of what I mean data analysis. We do these experiments, right? We get data, we want to make statements about nature based on that data. So, and our data in particle physics kind of stuff, at low level, it's something analogous to images, like raw counts in pixels, right, or something like that. And at the very high level, after we process them, it's particles, candidate particles that you can say, oh, I think in this one you have essentially a entry for every collision, and that collision you have a list of what particles you believe were in that collision. And so our analyses, typically what they do is they're looking for a particular final state, which means that a particular set of particles that arose because of some process that we're interested in. So I go through all the data and look for events that have those type of particles that I want in them. And then I try to go through and not only would I get type of particles that I'm interested in, right? Let's say the type of process I'm interested in, I'm going to get other processes that have similar type of features, so similar type of final state. And so then it's a process of being able to somehow make selections, as in throw out parts of the data so that I get a sample that's enhanced in the signal, in the thing that I'm looking for, and the backgrounds are suppressed. So that's analysis. Now we're going to go through this a little bit, okay? But that's basically the thing. I get data, I have to whittle it down, and then I get some sample, and that sample I have some amount of signal and background events. Signal being the process I'm looking for, and background is whatever can fit that process. And then I'm going to ask questions like, does this process actually happen? Did I have enough signal to say this particle actually exists, the process happens? Or if I'm done that and I know the process is there, maybe I'm trying to measure the mass of that particle. So find a mass and see if I can get what the mass of that particle is. Okay? So now the most important thing that actually ends up happening is that you can go do all that stuff and get an answer, but that answer means nothing unless you can actually tell you how confident you are in that answer. Okay? And so the most important part is actually going through that thing. And we have to, first of all, we want to estimate, some parameters, right? How many, signal events do I think is there? I want to measure the sort of the uncertainty on that measurement. And then, so I do process, I say, oh, I think I see 10 signal events. Then I do an analysis, say, I think the error on that is 5. And then based on that, the last thing I'm going to say, knowing that there's 10 signal events, apparently, and the error on that statement is 5, can I say that process exists or not? To what degree of confidence can I say that process exists or not? Okay, so that's sort of the process. So let me just say the process of analysis. So I would say one, I'll say prepare the data set, which just really means to, take the data set and cut it, try to throw out the stuff that's not your signal and keep your signal, okay? So once you've done that and you want to do something, you want to do some sort of estimate. So for example, number of signal events. So I'm going to use this terminology because particle physics uses all the time, signal and background. Does that make sense to you guys? I'm always looking for a signal and there's a background. Right, so for example that. Then what I want to quantify the uncertainty on whatever I figured out. And then I want to test sort of the extent that the data is compatible with some hypothesis. There being, Susie or whatever. Okay. You came in late. I had some announcements. I don't want to repeat it again. I did it twice. But in general, when you guys come late, I always give announcements in the beginning of the class of what's going on. So you came late, ask somebody else. Okay. And I'll try to actually make a habit of putting announcements in the slides. So you don't need to do that, but I haven't done it yet.
Okay.
Make sure that I may even say something that's not in the slides, so make sure you always, if you come in late, make sure you put it on. Okay. All right. So then I want to talk about this part. So what are the sources of uncertainty that you could have? You could have, one source of uncertainty is sort of undeterministic theory. So, for example, quantum mechanics, it's deterministic, but in the sense that it predicts the probability distributions of things. Doesn't tell you what's going to happen to any given particle, tells you what the probability of something happening, right? So there is some uncertainty to that. There's only some precision by which you can make certain measurements or make certain statements, fundamentally because the underlying theory gives you that limitation, right? So there's that kind of stuff. There are things like random measurement error. So I'm measuring sort of something, and today I have 1,000 examples of that thing to measure, and tomorrow I have 1,100. Tomorrow I'm going to do better than I did today, just by luck, because there's some fluctuation in the number of things. There's some random measurement error. And then the third thing is things that are unknown. And this, there may be other sources of error, right? Now, when we talk in physics, we'll sort of, I'm going to put something in here. Here, there's sort of, I guess there should be a third, sort of, I say a fourth, I just call it systematic. There may also be error because, let's say I'm measuring length or something, my ruler is only accurate to a certain level, right? So I can't say I can measure something to micron precision when my ruler is, only good to a millimeter precision. Okay? That's we call it something called systematic. Okay? So those are the type of errors that we have to assess, right? All right, so that just sort of frames the problem. So let's now talk about a little bit about probability theory. So let's start with that. Okay, so imagine you have some set. We'll call this set S. Okay. And it has some subsets, A and B. Okay. For all A that's inside S, this is sort of, say inside, all A within S, then, okay, so let's think about, for example, this set could be, this sample of this class, right? And A of these could be male and female. Okay. And so the subset of A is male, subset of B is female, right? So I can ask then, what is the probability of observing anything, right? So the probability of observing anything in the set, I can define that as being 1. So, if the probability is that you guys are inside that set, any of you guys from A or B or anything is 1 by definition, right? But that also implies then the probability of A is less than is greater than or equal to 0, right? But less than or equal to 1, right? In fact, it's now, if A and B have no overlap, so there's no girls or boys and boys or girls in this case, right? I'll write that as the null set. Then the probability of getting A or B is the probability of A plus the probability of B. Pretty simple, straight stuff, right? Other things, the probability of getting not, so this means not in this notation, not A is 1 minus the probability of A. Same thing, then probability of A and not A is 1. And the probability of A or B is the probability of A plus the probability of B minus the probability of A. Probability of being A, B, and you don't want to double count. This is the probability of the things that are in both A and B. So in the case of boys and girls, it's a 0. That's why it comes out to be that. Okay. Okay. Now let's change our thought a little bit, and let's talk about conditional probability. So let's make it, for example, let's imagine A is computer science majors, and so which is a subset of people here, and B is people who already know Python. Okay, and so this clearly has a huge overlap between each other. Okay, so conditional probability is something like this. So given that people know Python, what is the probability of being an A? So this is different, right, than the probability of A. There's a subset of people who know Python, right? And I can write that as the probability of A and B over probability of just being B. This is called a conditional probability. And if A and B are what we call independent, that means that then I can write P of A, B as P of A, P of B. These are completely uncorrelated. Okay. There's no reason that there's no correlation. In this case, there is obviously a correlation, but hair color versus, let's say, major. There's probably not a correlation there. Right? So you can write that probability of that way. This is, you can write it that way. And so the probability of A, the conditional probability, and then becomes PA, PB over PB, which is this then PA. I'm just using that formula, plugging it, right? Because they're uncorrelated. Right? So, how do we interpret these probability distributions? There's a interpretation. You can think of this as some sort of a relative frequency of something happening. So let's say A, B, these are some outcome of an experiment, a repeatable experiment, okay? And then there, I can say the probability of seeing A then is the limit as n goes to infinity of the times that the outcome is A over the number of times I do the experiment. Right? So, I get a bag of marbles. I want to figure out what the probability is that the marbles are either black or white. I pull a marble out, it's black, pull another, then put it back in, do the experiment again, pull another one black, so on. If they all come out black, every time I do this, then it's pretty clear that it's 100% probability that there's a black. There's all the probability getting black balls 100%. And if I get a white ball once in a while, then this increases and this doesn't. Another way you can think of it is sort of a subjective probability. Where A, B, these are hypotheses, like true and false statements, okay? And then P of A in that case is some sort of degree of belief that A is true. That's another way of looking at this. So my hypothesis is that, whatever it was. So for example, it could be, like the Higgs exists. Okay. That's a hypothesis that does the Higgs exist. And then what I want to use this probability distributions for is to say how confident I am in whatever answer I have. So these are two different ways of using this probability distribution. Okay, well, let's talk about Bayes' theorem. So the conditional probability, we wrote that earlier. Right? I can write the reverse conditional probability of Now, these two are the same, numerator, right? So I can solve one and put it into the other. So if I do that, so what I can do is, I don't know what this is, but I'll solve for it here, and then stick it back in there. That tells me that P of A, B is equal to P of B given A, P A over P B. Okay, so let's think about what this kind of means. So let's say B is the data set that I get. The probability of, this is given this data set. Okay? So given this data set, what is the probability that there's a Higgs? Okay? So how I can evaluate that is, I can go and do maybe some simulation and say, look, if I do this whole analysis on the simulation and I put Higgs in there, the probability, when I know there's a Higgs in there, of actually getting a data set like this is so much. I can do that through simulation. So there's a reverse. Assume there's a Higgs, what's the probability of getting the data? This I can do because I can do a simulation. Okay. How that's not the same thing because I have to account for the fact is how likely is it to get that particular data set, and how likely is it that Higgs actually exists given previous knowledge prior. So now I did this with two hypotheses. Let me quickly do it with n hypotheses, right? So I have it in the notes. I'm not sure if I want to take the time to derive it. Let me just write it down. I need to draw it out to make it understood. Same. So if you have more than one class, I'll do an example, of possibilities, you'll have to sum over each of those. So the standard example, it's not a good one, is that let's say you go and you do some sort of STD test, like a AIDS test, and it comes out positive. Should you panic? Okay. And to do that, you have to realize a few things. First of all, the prior probability of people having AIDS is something like 0.0001, so 1 in 1,000, let's say. Okay? So no AIDS is 1 minus that. Right? So is equal to 0.999. And then the test could be flawed also. So the test, the probability of getting a positive, let's say, given that you really do have AIDS, is, let's say, 98%. But you can get a negative given that you have AIDS, that equals 2%. Right? This is, you did the right thing. In this case, this is a false negative, right? So something to consider, even when they say you don't get it, there could be a mistake. Right? And then the probability of not having AIDS could be, so to be able to predict that right, it could be something like this, and correspondingly
Are these real statistics or just the scenario?
I have no idea.
Wait,
I mean, I don't know what the false positive, false negative rate is for things, and I don't know the.
Is one of those, the last two lines, the one that have a negative one?
The last one.
Okay. So now let's use Bayes' theorem to say if I got a positive test result, what is the probability of that actually being true, considering all these facts, right? That there could be a mistake, and that it's really rare, actually. So the probability of actually having AIDS, given a positive result, is going to be the probability of a positive result given that you have AIDS. The probability of actually the prior probability of how many people, which fraction of people actually have AIDS, right? And then I have to sum over all the possibilities. So I went through and did this sum explicitly. Now, if I plug in all these numbers, I'm not going to plug it in, but this comes out to these. So there's a very high chance that if you get a positive result, you actually don't have it, and it's a false positive. And it's mostly because the prior is very, very small. The probability of somebody actually having AIDS is very, very small. But the chance of making a mistake is very large in comparison. Right? And that's why it comes out this way. Have you guys seen this stuff before? Or some of you have. Okay. Very useful things to know.
That's good to know.
All right, so if just taking Bayes' theorem and just rewriting it one more time, but in sort of some more abstract way, in the way that we will very often use it. Oh, I erased the part that I showed you. It's in the notes. So given some data set that you have X, the probability of any given hypothesis, right, is equal to the probability of that hypothesis, giving a data set that looks like yours, and the prior of that hypothesis being true, times an interval, I'm going to do it sort of continuous way, of if this hypothesis is something that's sort of continuous. Okay. So that's just a generalization of this thing to a continuous probability distribution. All right, so then a couple other things. So we're talking about continuous probability distributions. Let's talk about that. So the probability of x being in the range of x comma x plus dx, right? That's defined as f of x dx, where this is called a probability distribution function. Okay. So this is a probability of, having any specific value, but if you are in some range, you have to account for the fact that there's not one value in some range. That's what the answer is. Probability distributions should be normalized. So if I integrate these things, this is what I mean by normalization, right? So it's got probably 1 of being anything. If I want to go to discrete, the generalization of this is just p of xi, I'll call it pi, and sum of p of xi is equal to 1. It's just a discrete version of the same thing. Yeah?
Do we not have to worry about the complex conjugate for this type of distribution function?
They're all real.
No.
And you're thinking quantum mechanics. So here, these are the square averages.
Okay.
In quantum mechanics, this would be your a of x squared. Everything else. Okay. Let me define some other things. So imagine I have a probability distribution that looks like this. This is my f of x, right? So, what it says is that I'm going to draw, this is just like you did in the homework. I'm going to draw some random numbers, the most probable values here, right? And, less probable outside of range, right? There's something called, if I want to know what is the probability of getting something less than this. So I want to draw a number with the probability of being getting less than this. You can just integrate. You can say the integral, that's equal to the integral from minus infinity to x of f of x prime dx prime. And I can call that some f of x. And this is called a cumulative distribution function. Just so you can see these words, nothing fancy, it's just. And to be clear, this is just an integral, right? So f of x is equal to d capital F of x dx.
And those are f of x prime and dx prime?
Yeah, yes. It's just because I need to sign my header, so. It's because I need to check that one. Now, the probability distributions that you guys will see in data would be, actually, how do you see those probability distributions? Well, I described to you, you do this, the example of the bag, right? You pull marbles out of the bag and you count how many times. Well, you can do that in some sense by just, looking at your data, right? And so, for example, let's say the group age distribution or the grade distribution in class, what I can do is I can histogram that. And what I mean by histogram is that here, this is a continuous distribution, right? This is a theoretical continuous distribution. But if I go and actually take data, what I can, to be able to get that back, I'm going to break this into little pieces of dx width, right? And every time I get a value of x within that particular range, I increment this by 1, right? And I go through my whole data set, and I'll get something that maybe looks like this, okay, which roughly follows that distribution. Okay? So you can look at, if you want to look at the probability distribution of something, you have a data set, all you got to do is histogram. Okay? And in the limit that you have infinite number of measurements, and this delta x gets small, this becomes this. Right? So you can say f of x, so I'll call this n of x, this thing, right? Then f of x is n of x over n, I have to divide it by delta x. And the limit that these things, this goes to 0 and this goes to infinity, this is perfect. You can have multivariate distributions. This thing could look like some f of x comma y dx dy. Okay. If x and y are independent, then f of x, y can be written as f of x, f of y. There's no correlation between them. So let me just define then some things that you should have already sort of used, which is things like the expectation value. Sort of like, what do I expect to get on average if I make some measurement over and over again? Okay. So the expectation value, we can write it as E. I'll say expectation value of x. So I'm going to do some experiment and I want to know what it is. I'm going to measure x. What is that? That is integral of x, f of x, dx. Well, define that typically you use mu as the expectation value. The variance is well, I should just move this right. It is the expectation value of x squared, so just squared in there, minus mu squared. And this is sometimes referred, we write as sigma squared. And that this, if you go through it, is also the expectation value of x minus mu squared. It's the same. And the standard deviation which is sigma, is the square root of the variance. And that's exactly what we needed, remember, for the shifting and everything that we just did. When you, after I'm by to calculate the variance, it gave you this, which is a square. So when you go back and look at that, now you can understand what those things mean a little more. Talk about covariance. So the covariance of between x and y is the expectation of x, y, where the n-dimensional version of this has dy, dz, just add the additional ones, right? Minus mu x, mu y, given the definition we had before. You can use this to calculate something called the correlation coefficient. I'll call that rho xy is the covariance of xy divided by sigma x, sigma y. And this is sort of an interesting thing because it tells you, you can use this to sort of predict some things. You can say, look, I know, what the probability of this particular xy is. If I increase x by so many sigma, about half of the sigma of x, how many sigma does y change? And so this tells you how many, so this number will tell you. Okay, so if I move, if this thing's 0.3, and if I have x go up by 1 sigma, then y will change by 0.3 sigma of y. That's what this means. If these guys are independent, this integral that I'll do will, these will be independent, right? So this is going to give me, the function itself is going to be, f of, I guess I have it here. It looks like this. Each of those integrals, right, I can pull separately, and that integral will be x, f of x integral, and y, f of y integral, right? Yeah. And those are just mu x and mu y. And so when you then calculate covariance, this will be mu x, mu y, minus mu x, mu y becomes 0. Okay. So the covariance is a measure of how correlated these things are. Okay. I'm going to stop there. I have lots more in the notes. I will come back to this as we need it. I will probably do a couple of more pages of it next time I see you guys. But it goes further, and we'll come back to some of these concepts as they become more and more relevant. I just wanted you guys to have a basic understanding of things because we're going to start writing things. I want you to know what it means. Okay, you don't have to have, this is the sufficient level, but just what these things mean have to be defined for you one time. Again, these notes are posted. You're welcome to go through them. And so, Garrett, I don't know if you saw this, but you gave me too. Everybody knows that they lab 1 and 2, they have to do their best job, and I'm going to take a snapshot and grade you on that before the lab on Friday. On Friday, we're just going to have a lab, so bring your laptop. Okay. Okay.
And you'll have the solutions posted.